So hi, my name is Kai Sheikh. I'm applying to the University of Washington, and today I'll be introducing a little trick called differentiating under the integral. And so this is a nice trick, and it'll allow us to calculate two famous integrals, namely the Gaussian integral, which is this, and the gamma integral for an integer. So this is this is a typo. This should actually be negative infinity. Although, of course, since e to the minus x squared is an even function of x, this is just twice the integral from 0 to infinity. So we won't worry too much about that. So let's start out with this integral, which we'll call gamma of n, to sort of illustrate this technique. So basically the idea is we want to introduce a parameter t, which allows us to compute this in a more clever way. So in particular, we'll consider the function e to the minus xt, or the integral rather, where t is just a parameter here. And the reason this is convenient is because this is easy to integrate. This is just, minus t is just like a constant here. So this is just e to the minus xt over minus t. And well, at infinity this goes to 0 because the exponent gets infinitely large. And at 0, this exponent is just going to be 0, so the e part will go to 1. So we get minus 1 over t. So that's just 1 over t. And I should say that we're interested in t positive, is why when x goes to positive infinity, the exponent goes to minus infinity, and thus it goes to 0. So now, the key observation here that we're going to need is that when we take ddt of this integral, the first fact that we're going to use is that we can bring this derivative inside and make it a partial t. And intuitively, what's going on here is this integral, when we integrate with respect to x, we're sort of getting rid of x. It's no longer a function of x because that's just our variable of integration. But it's still we can think of it as a function of t. So therefore, this is sort of a valid operation. But when we bring the t inside, we're sort of going before we've integrated out the x. So that's why we need to make it a partial. And so using this fact, well, we're going to sort of calculate this, and what it is, it's just minus x e to the minus xt. We're integrating this. And the reason this is useful is because this sort of is hinting at our original gamma function in the case where t equals 1. So in particular, if we take the derivative with respect to t n times of this function, this is just going to bring down a factor of minus x n times. It's going to be minus 1 to the n, integral from 0 to infinity, x to the n, e to the minus xt dx. And so evaluating at t equals 1 will just give us minus 1 to the n gamma n, because we've defined gamma n up here as integral from 0 to infinity of x to the n e to the minus x dx. And the key point here is that this thing on the left-hand side we can calculate in a different way. Namely, this was easy to integrate, right? We've already computed that this is 1 over t, so we just need to take the nth derivative of 1 over t. And well, this is easy enough. So we have t to the minus 1. So if we differentiate once, that's going to yield negative 1 t to the minus 2. Differentiating again will give us minus 1 times minus 2, t to the minus 3. And you see what's going on here? If we differentiate n times, this is going to give us minus 1 minus n, t to the minus n plus 1. And this is, of course, just equal to minus 1 to the n factorial t to the minus n plus 1. So now we've shown that minus 1 to the n gamma n equals minus 1 to the n factorial t to the minus n plus 1. Although, sorry, that's not quite accurate. We've showed that this, when this is evaluated to 1, so this term just becomes 1, and canceling these sign factors, we get that gamma of n equals n factorial. And I should point out that I've defined gamma n slightly inaccurately. It should actually be, well, I think I've defined it accurately. But I mean, sometimes there's a, maybe don't follow my definition of the integral too closely, because sometimes it's defined like, I think it's written like gamma of s equals integral of x to the s minus 1 of e minus x dx is what you might see more often. But anyway, so that's I think a sort of slick proof that the gamma function evaluated on an integer is n factorial for the integer n. So now we're going to turn to the Gaussian integral and sort of apply the same idea, which is basically sort of a clever trick to reduce our problem a little. And so the integral we're going to be interested in is this, which is half the Gaussian integral, as we've already said, because we're just using the fact that this is even. And so the integral we're going to consider instead is going to be this. So we're going to introduce the parameter t in this way. You might wonder, why are we introducing a denominator? This is basically because when we differentiate with respect to t, we're going to bring down this factor, sort of a constant factor with respect to t, down, and it's going to kill the denominator. So we're going to be left with something nicer. So in particular, taking the derivative with respect to t is going to yield, let's write it out. So we're going to get minus 2t from this, times a constant, which is going to cancel the denominator, and a 1/2, which is going to cancel the 2 from the minus 2. So it's just going to be minus t e to the minus t squared times the same stuff. And now what we can do is we can pull out this t and the minus t squared. So this is e to the minus t squared over 2 times e to the minus t squared x squared over 2. Okay, 2. Sorry, I should have said, we're going to consider actually a slightly modified form of what I wrote here. We're going to consider this over 2. So that's the more standard form. So what this is now, let's rewrite this. This is minus t e to the minus t squared times the integral 0 to infinity of e to the minus t squared, sorry, let's write tx squared over 2 dx. And what we'll notice is that this is just like, we can get this by a change of variables. So we'll set, in particular, we'll set u to tx, and then so we have minus t e to the minus t squared over 2 times this integral 0 to infinity of e to the minus tx squared over 2 dx, and then we'll set u equal to tx, so that du equals t dx, and this allows us to transform this integral to 0 to infinity e to the minus u squared over 2. So dx is dx is du over t, right? So now what we're going to get ultimately is this 1 over t is going to cancel this t, and we get minus e to the minus t squared over 2 times just our Gaussian integral again. So this is what we're going to call I without this t. So this t has been canceled. So what we have now is this, So and what is this? So let's recall what this was. This is the t derivative of this function 0 to infinity e to the minus t squared 1 plus x squared over 2 over 1 plus x squared dx. And let's call this f of t because it's really it's a function of t that we're sort of interested in. So let's call this f prime of t. And so now what we'll note is this is sort of the Gaussian function all over again. So what we'll notice is if we take the derivative with respect to t of f prime of t from 0 to infinity, this is we're sort of going to recover the Gaussian integral. So it's going to be minus integral from 0 to infinity of e to the minus t squared over 2 dt times I. And this is, of course, again, just the Gaussian integral. So this is, let's move this up a little, minus I times I, or minus I squared. But another way we can compute this is, well, this is sort of the fundamental theorem of calculus tells us that integral from 0 to, let's say, c of f prime of t dt, it's just f of c minus f of 0. And now we can actually compute these two parts. So f of c, what's f of sorry, not f of c, what's f of 0? F of 0 is plugging in t equals 0 into this sort of weird looking integral that we had before. So it's, just to recall what the integral was, it's integral from 0 to infinity of e to the minus t squared 1 plus x squared over 2 over 1 plus x squared dx. So when we plug in t equals 0, this e term is just going to go to 1 because the exponent is 0. So we're just going to have integral from 0 to infinity 1 over 1 plus x squared dx. And this is arctan of x from infinity to 0. And arctan of infinity is pi over 2. And arctan of 0 is 0, so this is just pi over 2. On the other hand, f of infinity, what's that going to be? Well, when we send t to infinity, we'll notice that 1 plus x squared, this is a positive quantity. And when t goes to infinity, positive infinity, well, or negative infinity for that matter, this t squared term is going to blow up. So the exponent is going to become infinitely negative. So this whole thing, the e term is going to go to 0. And thus the whole integral goes to 0. So this is 0. So the fundamental theorem of calculus tells us that in the limit that c goes to infinity, let's write it like this, is just f of infinity minus f of 0, which is 0 minus pi over 2, or negative pi over 2. But we also showed, recall, we also showed that this was equal to negative, the integral we're interested in squared. So we're going to get, canceling the signs, we get that I squared equals pi over 2, or I equals the square root of pi over 2. And recall that this is just our, I was just our Gaussian integral negative x squared over 2 dx. And so I think this is a nice alternative to the usual approach. And if you're not familiar with the usual approach, it's just using change of variables to polar coordinates. So we're going to introduce some variable y. We do something with the Jacobian, and we calculate I squared. And this gives a sort of clever alternative. Of course, you might not have thought of this, is maybe the one issue we should worry about. But it does give a very elegant way of deriving some more complicated integrals, like the damped sine integral, for example, and others, given a little bit of sort of leaps of intuition. So thank you for listening. I would say if you have any questions, ask me, but of course this is a recording, so I can't. But yeah, thank you for watching, and yeah, I hope you learned something.